So once again, good afternoon. Uh, Today I'm going to teach you about how to simulate a beam problem. So in our case, we are considering a cantilever beam. As you know, we fix one end and apply a force on the free end. So I want to use ANSYS APDL to solve the problem. So let me first create the software. So it's always better to start with the mechanical APDL product launcher. So use this option. So in the meantime, just I want to discuss about this problem. So this is exercise number 8. Here you are having a cantilever beam. So total length of the beam is 750 mm. You are applying a 1 kilonewton force on the free end. If you closely observe the cross section, it is 50 by 50, and you need to find the stresses, reaction forces, and the vertical displacement. They already provide the material properties. Young's modulus is 210 gigapascals, and Poisson's ratio is 0.25. So as already told, so if you use any software, generally we divide the problem into 3 steps. 3 steps are the pre-processing, solution, and the post-processing. So I want to discuss all the steps initially, then we'll move to the software. So in the pre-processing, first we need to define the type of element that we are going to use. So since it is a beam problem, I'm assuming beam element. Beam element is a 1D element. So each node could have 6 degrees of freedom. That is translation along XYZ and rotation along XY. Rotation with respect to XYZ axis. So theoretically, if you distribute the beam in 2D space, then each node should have 2 degrees of freedom. That is translation along y-axis and rotation with respect to z-axis. Okay. So we assume that beams are subjected to transverse loads or bending loads, and deformation is along the transverse direction, deflection. Am I clear? So I'm assuming beam elements, and under beam elements you have 2 types. One is 2-node element and the other one is 3-node element. Beam 188 is a 2-node element, and beam 189 is a 3-node element. So I want to consider a simple element. So I'm opting for 2-noded beam 188 element to solve the problem. Then generally, in case of beams, we don't use any real constants. So there is no need to provide anything there. Material properties, as usual, it is specified now. So using these 2 constants, I can only define linear elastic, isotropic material. So I'm assuming the material as linear, elastic, and isotropic. So you need to provide the Young's modulus and the Poisson's ratio. So Ex is represented. Ex actually represents Young's modulus, and PR xy represents the Poisson's ratio along xy plane. So after defining the material properties, we need to define a section. Okay, if you observe the beam equation, no, you need to calculate the value of I. the value of I depends on the shape of the cross section. So definitely for a beam, you need to define a cross section. In case of bar elements or link elements, we only provide the real constant because it doesn't require the value of I. There, you only need the value of A, and A remains constant and it doesn't depend on the type, shape of the cross section. So I will show how to create a cross section. So if you closely observe now, the cross section is the square in our case, or otherwise width is the value of B is 50 mm and value of D is also 50 mm. In ANSYS, they are represented as B and H values. H is the height and B is the width. So after defining the section properties, we need to create the model. So it's a simple model now. So that's why we are using the options that are available under ANSYS. So in our case, we are creating 2 points. Points are nothing but the key points. So this is key point 1, and this is here. I'm going to create one more key point, which you can name it as key point 2. So if you closely observe now, the total length of the beam is 750 mm. So initially, the key point is at the origin. I assume it as at the origin. So it should be 0, 0. After that, the next key point should be the x value is 750 and y value should be 0. So by that, after creating the key points, I'm going to create a line between those 2 key points. So I'm using line option for that. After creating the model, I need to discretize the model. So in the previous case, while discussing about the truss elements now, or truss problem now, we are assigning each element for each truss member. But in this case, you can actually divide the whole beam section into some parts. So for my convenience, I want to assign 75 elements. So each element length will be 10 millimeters. So for my convenience, I am assuming it as 75. You can also, instead of going for size control and defining it as number of divisions is equal to 75, you can also specify the element length equal to 10. The result will be the same. So for my convenience, I just simply use number of element divisions is equal to 75. So after creating the mesh, you need to apply the boundary conditions. Okay. So I need to apply the boundary conditions. So here I need to fix this point. So we can select that particular key point and apply, like we can fix all the degrees of freedom because this end is already fixed. On the other end, so that is you need to apply a load on a key point 2. So the load, since it is acting in the downward direction, that is represented by Fy. Okay, it is acting in the downward direction. So this is Y, and the total value is 1 kilonewton. So since we defined the Poisson's ratio, Young's modulus in terms of Newton per square millimeters, I'm putting the force in terms of newtons. So you need to provide units should be consistent. All the lengths are expressed in terms of millimeters and forces are expressed in terms of newtons. So once you apply the boundary conditions, it is ready to solve. So you can create a new analysis type. In our case, since it is a structural problem, we are going for structural static analysis. You're going to create a load step, and after that, you're going to solve the problem. So once you get the results, you can move to post-processing, and you can find the deflections as well as you can draw bending bending moment diagrams, and shear force diagrams. So let me enter into the software and solve this problem. Okay, so once you select that option, no, like mechanical APDL product launcher, so you'll have a window like this, as already told. So now I want to create a new working directory for the problem. So I'll simply say exercise 8 cantilever beam. I'm creating a new directory. Once again, I want to create a job name. Exercise 8 cantilever beam. So generally, it doesn't allow spaces when you create a job. Okay, so that's why better to not leave any space between the letters. So after creating this, you need to run the software. So once you click run option, mechanical APL just by running that, you can open the software. So now this is the graphic user interface of the software. So since the analysis is of structural type, so I want to define the preferences as, let's select that option and opting for structural analysis. So select this option, click OK. So now let me start the pre-processing. Initially, I will start with assigning the elements. So just click here, define the element type. So I'm selecting element type. I need to add an element. So let's select add option. Let's click add. So since I didn't select any, so this element type window remains, I mean, there's nothing inside here now. So you need to add the element. So since we are dealing with the beam problems, I'm selecting beam as the element. As already told, under beam, you have two types of elements, two noded 188, three noded 189. So three noded means the element has a extra node at the middle. So for my convenience, I'm opting for two node element. If the structures are very complicated, then you can opt for three noded element. So generally, three noded elements are more precise, but since the problem is very simple, you'll have the same solution. Okay, you don't have any difference. So let me offer two noded 188 element. Click OK. Then close this. So I already selected an element type. So after selecting the element types, so there is no need to define the real constant. Okay, let me check. So if I just want to create a real constant for that, it will show a warning. Okay, let me select this. Let's add a real constant. So when I select the beam element and click OK, so it says that the beam element type does not require any real constant. So you can avoid real constants, there is no need to define it. So after that, let's add the material properties. So I'm choosing the material property. Here I'm using material models to create the or to enter the material constants. So now I'm opting for a structural, linear, elastic, and isotropic. Okay. So they specified the Young's modulus as 210 gigapascals now. So I want to convert that into Newton per square millimeters. So the resultant will be 210 into 10 power 3. Variance ratio, they specify it as 0.25. Then click OK. So now after after creating the material, you can specify the cross section. Okay. So I'm opting for, let me close this window. Okay. I'm creating a section. So you need to select this option, sections. So since we are dealing with the beams, select beam option. And if you closely observe the cross section, it is very simple cross section. So it will be available under common sections. So I'm opting for common sections. Now you can choose the particular cross section. See here, you have this option subtype, and if you drop down here, you will have different cross sections. Okay, like I cross section, C section, and so on, L section, and so on. So since we are dealing with a solid structure, so I'm setting this rectangular section. Okay, and here it clearly says this value is, the width is represented by B, and the height value is represented by H. So now you need to specify the values. The value is 50 by 50 now. So let's add a value there, 50. Okay, since they are in millimeters now, so everything should be, line should be in millimeters. So that's why I put it as 50 millimeters. You can also view the, you can go for preview so that you can actually see the values of I values, say I, and so on, area cross section and so on. So once you, if you press preview now, it will show the cross section. See, this is the cross section. So this is the centroid, and the I values with respect to different axes will be calculated here. Okay, so that's why there is no need to specify the area of cross section as a real constant in this case. Once you specify the shape section, automatically it is going to calculate the area of cross section. Along with that, it is going to create calculate the value of I. See this area moment of inertia. I is nothing but area of moment of inertia. Okay, this is how you can, if you want, you can change the shape and recalculate it. So let me close this. So if you want to continue, just use plot and use replot option. So you'll have the window. Okay. So after creating this now, you need to create the model. So I created the section. Now I'm going to create the model. So under modeling, you can use this option create. Initially, I want to create key points. So let's start with key points. And I'm going to create the key points using the inactive coordinate system. So I'm selecting this option, inactive coordinate system. You can name the key points, or otherwise by default it will start from 1 and randomly it's going to continue. Okay, in a sequence. So initially I want to create a point at the origin. So the x should be 0, y should be 0, or otherwise you can leave them as empty. So empty space, it will pick it as 0. Okay, I want to leave it like this. I'm pressing apply so that I don't close the window, and I can automatically create the next one directly. Okay, so I'll press apply. A node will be created. Then here I want to create the next one, node point 2 or key point 2. What's the value? X value should be 150, sorry, 750. Y value is 0. That value remains 0. Okay, here I'm going to create OK. So point will be key point will be created, and the window will be closed. Once you press OK. If I press apply, then don't press OK. You need to press cancel. Okay. If you press apply, then OK, it will create two key points with the same coordinates. Okay. Let me click OK. So now I created two key points. This is one key point, and this is the other one, which is actually merged with the origin. That's why you are unable to differentiate it. So if you want to actually check whether you created it correctly or not, you can go to list option, and you can pick key points. I can go for coordinates, attributes, or coordinates only. Since I didn't add any attributes, I'll go for coordinates only. Let's press this. See, now it is listing two key points, key point number 1 and 2. So key point number 1 has a coordinates, x coordinates are 0, 0, 0. Key point 2 has x coordinates 750, 0, 0. Who is that making noise? Rohit, please mute yourself. Someone called Rohit and asked him to mute it. Am I clear? Okay, let me continue. So after creating key points now, I want to create a line between those two key points. I'm using line option. Let's select line. So I want to create a straight line. So I'm opting for straight line option and select these 2 points. I'm selecting these 2 points. Click OK. So now we created a line. Okay. So after this, I need to assign. I want to discretize the model, or I want to mesh the model. So go to meshing option. So before actually creating the mesh, I want to check the mesh attributes. Let's press this mesh attributes option. I can pick all the lines. So you have only one, so there's no problem. And now I want to assign the material. So you have only one material. So by default, it's picking one. Element type. Element type is beam 188. And here you need to select the element section. See here, I don't find the element section. So what to do? Maybe I didn't create the section properly, so that's why you don't have that option. Let me close this. Click on cancel. Okay, and move back to sections option. Use beam, common sections, and re-enter the values. Say 50, 50. I think I didn't press OK. I just went for preview. Okay, that's why I didn't create the. It didn't create a section. So let me press OK. So now move to machine. Once again, select all the lines. So now if you clearly observe now, section 1 is mentioned here. So everything looks good. Click OK. So after creating this now, after assigning the mesh attributes, you can actually define the size of the element. So I will opt for size controls. Use manual size. Since you have lines now, I'm opting for lines. You can pick lines or all lines. I'm selecting all lines. Now you have two options. Like you can specify the length of the element, or you can specify the number of divisions. So in the previous case, I specified length of the element as 1 now, or sorry, number of divisions as 1. So here, for my convenience, I want to specify it to 75, since the total length of the bar is, sorry, beam is 750 mm. So each element length will be 10 mm. So you can add 10 here, or otherwise 75 here. Both are the same. So I'm opting for 75. Sorry, 10. Click OK. So now it's going to show the preview. So if you count this now, you'll have 75 elements on the whole. Okay. So I just define the size. Now let me mesh the beam. So I'm opting mesh option. I'm selecting lines. Let's select the line and click OK. So now the model is meshed. I want to cross check whether it is creating 75 elements or not. So I will go to list option and use elements. I'll offer nodes and attributes. So if you clearly observe now, so total number of elements should be equal to 75. See here, it will specify all the details about the elements. So for example, element 1 is between node 1 and 3. Randomly, you take element 30. Element 30 is created between node 31 and 32. So similarly, element 75 is created between node 76 and node 2. Okay, if you want to actually see the number beside the nodes or elements, you can go to plot controls, use numbering option, and here you have different options. Like I can view the key point numbers by switching on this. Hit apply. Okay. Or if you want to view the nodes, so I'm opting for on. Click OK. See here total. If I zoom this now, on the whole you have 76 nodes. Am I clear? You can zoom in and zoom out by using these options. See, node 2 is at this end of the beam. Node 1 is at other end. Okay, in between you have some nodes, and in total you have 76 nodes. So since they are very congested, they don't looks good. So let me unselect them. So once again go to numbering. I'm opting for, I want to unselect this. Click OK. So I don't view the key points now. If you want to view the key points, you need to plot lines. Okay, when I plot lines, you can view the key points, or directly you can plot the key points. Then the line won't be visible, only key points will be visible. It doesn't have any sense, so I want to just, okay, so this is actually a line. It's not a, these are not elements. Okay. So after meshing the model, you can, yeah, you need to apply the loads now. So I want to move to load option, loads. So here you can define the type of analysis. Loads option will be available under solution also. Okay, you can create analysis type under solution or in this step. So I'm going to create the analysis type here itself. Let's select analysis type. I'm creating a new analysis. So since this is structural problem, I'll go for structural static analysis. Click OK. Let's define the loads. So I'm going to apply the loads. So press apply. So since the loads are of structural type, I'm opting for structural. So we already discussed about the boundary conditions, no? So this end should be fixed, and here you are going to apply a concentric load which is acting in the y direction, negative y. So initially I want to opt for displacements. Let's select displacement option. You can apply the constraints on the nodes or on the key points. So because they are congested, I will go for key points. I'm selecting the key point 1. So key point 1 should be fixed. So this is key point 1 and this is key point 2. Click OK. So I can go for all degrees of freedom. So since this is fixed now, I can go for all degrees of freedom. But if you have roller support or simply supported conditions, then you can't go for all degrees of freedom. Okay, there you can use these options. Wherever you want to constrain or fix, you can select those degrees of freedom and make them as 0. So in this case, since this end is fixed, I'm considering all degrees of freedom. As already told, each node has 6 degrees of freedom now. Displacement, so ux, uy, uz are the displacements along x, y, z respectively, and rotation, rot, xy. Rot, x means rotation along x-axis. Similarly, you have 3 degrees of freedom related to rotation. Okay, so if I opt for all degrees of freedom, naturally all the degrees will be fixed. So if you leave it as blank, it will consider as 0. So that's why I'm just closing the window by selecting all degrees of freedom. So this symbol indicates that it is picking all the 60 degrees of freedom are constrained. So after constraining the key point 1, I need to apply a force on key point 2. So to apply a force now, I'm opting for force option. I want to apply it on the key points. Let's select key point. even though if I click it here, the points won't be selected. We don't have any key points here. Okay, I only have 2 points. Click OK. So the force is acting in the y direction now. So I'll opt for Fy. Suppose if you have moments acting at a particular point, then you can use these options. At present, we are only related to a concentric force. So I'm opting for Fy. So if a force is acting in a particular orientation or an angle, you can resolve that into 3 components: Fx, Fy, and Fz. And you need to individually allot the values. So in our case, the force is actually acting in the negative y direction. So that's why I'm opting for Fy. Let's add a value here. It should be minus. This 1 kilonewton now. I want to change that into newtons. We need to specify all the forces in terms of newtons. Because we specified the Young's modulus in terms of newtons per square millimeters. Click OK. So this arrow actually represents the force which is acting in the downward direction. So after creating the force, we are done with the pre-processing. Now let's solve this problem. See here, you are picking, actually this node is also accidentally. See, you have an arrow here now. So if you want to remove the load, so I go back to load step. Okay. So under define loads, you have delete option. Okay. I'm opting for delete. Structural forces on key points. I'm unselecting this option, this key point. Click OK. I can opt for all. Click OK. So now if you see, only concentrated load at key point 2 is still there. If you want to cross check it, go to list. So here you find loads option now. I can choose forces on all key points. Let's select this option. See, at the key point, you have node which is going acting along Fy direction, and the value is minus 1000. It is newtons. You can cross check it whether you did correct or not. Okay. So after this, let me solve the problem. Go to solution option. We already created the analysis type now. There is no need to create once again. Simply go to solve option. I'm using I want to solve the current load step. Let's select this option. If you clearly observe now, it says that the problem is of 3D type. They are dealing with 6 degrees of freedom, that is UX, UI, UZ, and also rotations along X, Y, and Z directions. Analysis type is of static. Okay, steady state. By default, you will get a symmetric matrix as the global stiffness matrix now will be symmetric. Okay, let's close this window and run the program. So it says solution is done. So since it's very simple, you'll get the solution in seconds. Close it. So now you can actually see the results. So I want to view the deflections along the beam. So I offer general post processing, and here I'm opting for plot results. Let's select this option. I want to see the deform shape. Let's pick this option, deform shape. You can select one option, any one from these 3. I'm opting for the last one. Click OK. See, the white line represents the undeformed beam, and the blue line represents the deformed beam. Okay, you can also plot contour plots by using this option. I want to view the what to say the displacements along the beam. So I'll opt for nodal solutions. So since the displacements are calculated at the nodes, that's why I'm opting for nodal solution. Okay. So under nodal solution, I'm picking the degrees of freedom as the option. And here I want to view the vector sum of the displacements. I'm opting for displacement vector sum. Click OK. So if you clearly observe now, the deformation or the deflection at the free end is more, is the highest. Okay. And since this end is fixed, the value is 0. Okay. All the values are positive because we went for vector sum. Suppose if you want to show the displacement along y-axis, you can pick this option, y. Okay. So here, yeah, the minimum value, since this they are in the downward direction now, so that's why it is picking as negative, and the maximum value is 0. 0 means this end is fixed, so that's why the maximum value is 0. Okay, don't get confused. So if you pick the vector sum, the value will be always positive. So now if you want to view the stress distribution along the beam, you can offer once again under plot results, use contour plot, go for element solutions. Okay, I want to select show the stress distribution and begin the formative stress. Click OK. So the stress remains constant over the specimen. So if you want to view the you want to draw bending moment diagrams and shear force diagrams now, you need to create a element table. So to create element tables, you need to select this option element tables. So I want to define a table initially. Let's add. Okay, here I want to go for by sequence numbers. Calculate the bending moments. I want to opt for the value should be 3. Click apply. So similarly, you need to get the remaining 6. So actually each element has some preset values. You need to pick the same numbers. I will show how they work. 6. Click OK. Add once again by sequence number 16. Add sequence number and 19. Okay. So I will now discuss about what are these things. So I want to use help. See here. So this is the information related to beam element 188. Okay. You can go to ANSYS help and select beam 188 element. Under output, no output parameters, no. Yeah. See here, if you want to get the values, no. So we are using sequence numbers, and to get moment along z-axis, you need to select the I value as 3 and j value as 16. So these are all predefined. Okay. So I want to calculate moment with respect to z-axis now. So that's why I opted for 3 and 16. Similarly, the shear force now, shear force is acting along y direction, SFY. Okay. So here I value should be 6 and j value should be 19. So that's why I selected I created a table like 3, 6, 16 and 19. 3 and 6 are related to bending moments. 6 and 19 are related to shear forces. Okay, once you create the table, close the window. So now I want to plot the bending moment and shear force diagrams. So once again, go to plot results, use contour plot option, and here you have line element representation. So let me select this option. Sorry, line element results. Okay. Let's pick that option. And here, as already told, at node I, it should be 3. Node J, it should be 16 to actually show the bending moment diagram. Click OK. So now you can clearly observe now. So this is the bending moment diagram for the cantilever beam. If you want to plot shear force diagram, let's use the same option, line element results. So here I need to pick 6 and 19. I'm opting for deform, undeformed shape. Click OK. See the shear force is constant for the span. So this is how you can actually draw shear force and bending moment diagrams. So up to now, any doubts? You can also list the results. Okay, if you want to list the results, go to list option, list results. I want to list the deformations at particular nodes. So I'm using nodal solutions. Degrees of freedom. If you want all the degrees of freedom, you can pick. Yeah, it's better to select some now. I don't want to all. If I pick vector sum now, automatically these values will be represented there. So I'll opt for displacement vector sum and rotation vector sum. I'm picking these two options. Click OK. So now if you close the observe this table now. So randomly if you pick node number 20, so the rotation will be 0, 0 and sorry, yeah, these are the rotations along xy directions, which are naturally 0, and z they are varying, and this is the vector sum. So similarly, so these are all related to rotations. Let me close this. If you want to have displacement, no. Once I select nodal solution, I will go for vector sum. Click OK. And these are all deflections or displacements along XYZ directions. Actually, X and Z should be zeros. Only Y is going to vary. Okay. And this is the vector sum. So on the whole, you have 76 elements. It also shows the maximum value. Okay. So maximum value is minus 1.289. So this should be assumed as millimeters because we all we always represented the lengths in terms of millimeters. So the values that you get should be expressed in terms of millimeters. Any doubts? So I'll give some time. If you have any doubts, you can put it in the chat box. So just save it. Otherwise, you may lose the data. So I want to save the database. If you want to save the database, just press this option. Any doubts? So let me solve one more problem. Okay. So this is stepper bar problem. If you closely observe now, you have two elements, bar elements. So here the area cross section is twice than this. So let's assume area cross section as 200 A. Value of A is 200. So for this element, area cross section is 400. Young's modulus, assume it as 210 gigapascals. Length of the element or at the bar, I assume it as 100 millimeters or make it 500 millimeters. force acting at this point is assumed as 10 kilonewtons. Okay, let's solve this problem. If you clearly observe, these two ends are fixed. So how do you approach this problem? So initially, I will create three key points, key point 1, key point 2, and key point 3. Then I will create two lines, line 1 and line 2. We are going to create two real constants. Okay, real constant 1 to specify the area of cross section of this element, and real constant 2 to specify the area of cross section of this element. So after creating real constants, you can you can move to meshing, no? So before meshing, you need to assign the attributes, mesh attributes. So let me solve this problem. I'm assuming area of cross section A, the value of A as 200. In this case, value of L as 500 mm. Value of P is 10 kilonewtons. Okay. So let's solve that problem. So I'm done with this now. I want to save it and move to next option. So I'll say clear and start new. Click OK. Even I want to change the directory, working directory. Let's select this option. So I will use this directory as the working directory. Click OK. So now let's start with pre-processing. So once again, I want to define the problem as structural. Click OK. Okay. Use pre-processing. First define the element type. Add an element. So since this is a stepper bar now, I'm opting for linked elements. I'll offer element 180. I want to choose the first one. Click OK. Close the window. Then move to real constants. I need to define two real constants now. Let's add the first one. I'm selecting the element type as 180. Click OK. See here, I'm using the new version. The previous case now, in the previous class, I used ANSYS 16 version. Now I'm using the student version 2020. So I can't use real constants here. Let me go for sessions. Okay. Yeah. So under sections now you have a link option. So I'm opting for that link option. Add. Okay. So here I'm adding 400 as constant 1, or you need to name it now. Yeah. Link area now is 400. Click OK. I need to add one more now. Click add. I'm representing the ID. So it should be 1 and 2. You can use 1 and 2, but I use 400 and 200 so that you can separate it uh, differentiate it very easily. Click OK. Area of link should be 200. Click OK. So now after creating the session properties, now let me create the material properties. So I assume both the bars are of same material. I'm using material models, select structural, linear, elastic, and isotropic. So I want to define it as 210 megapascals. So it should be 210 e power 3. E power 3 is 10 power 3. Click OK. See here, I didn't specify the value, no, Poisson's ratio value. So that's why it is assumed as 0. Let me cancel this. If you want to edit, no, just double click on this. So this value should be 0.25. Even if you take the Poisson's ratio as 0, it is valid because the Poisson's ratio value changes, varies from -1 to 0.5, no? You need to remember that it shouldn't be more than 0.5 and it shouldn't be less than -1. It should be between -1 and 0.5. So I'm opting for 0.25. Click OK. I'm closing this window. So after creating the material properties, no, I want to create the model. Initially, I will create the key points. Let's do it in the active coordinate system. So I'll assume the starting point. This point as the origin. So it should be 0, 0. So I don't want to enter anything. Just press apply. So then a node will be created at the origin. Next should be 500, 0, 0. Once again, I'll press apply. A new node will be created. New key point will be created here. Then I'll change it to 1000. Click apply. If I click OK, now I pressed apply, and if I click OK, then it's going to create two key points here. Just I want to show the difference. So that's why I created like that. So let me list the key points. Go to list option. Key points coordinates only. See here, my aim is to create only 3 key points, but accidentally I created 4. You can delete the key point by using delete option under modeling. Okay, I want to select this key points option. So see here, you have 2 key points, one or the other, no. But I know the number of the key point, no. So I want to remove key point 4. So straight away you can type the value here, key point 4, and click OK. So the key point will be removed. Once again, recheck it. Go to list key points coordinates only. Now you have only 3 key points. After this, I want to create lines. Okay, under modify, under modeling, create lines, straight lines. Now I'm going to pick the key points. You need to click twice, then only you can create a line. So you have 2 lines. Why I created 2 lines? Because the area of cross section of those 2 lines, area of cross section changes. So that's why I want to allot one element representing 400. Area of cross section is 400, and the other element with area of cross section is 200. So that's why I opted for 2 lines. So after this, I will go to meshing. I'll opt for mesh attributes. So now, since the area of cross section differs now, so I will use pick lines. I will allot the area cross section individually for those lines. So I'll offer pick lines. That the first one. Click OK. See here, area cross section should be 400 now. So I'll offer 400. Link element type is same, and material is also same. So that's why I'm leaving the default values. Click apply. Then I'm selecting this line. Click OK. In this case, the area cross section should be 200. Click OK. So now I added the real constants or the section properties to that. You can cross check it. Go to list option. I want to pick lines. Attributes format. Click OK. So it is only showing the length now. So let me mesh it and check it. Okay. So I'll go for meshing. I define the mesh attributes now. Let's use size controls. Once again, I want to choose manual size. Lines option. I want to allot one element for each member now. So I'll pick all the lines and number of divisions as say 1. Click OK. So I didn't mesh it actually. I just assigned the size. Now use mesh option. I'm selecting lines. I have to select both the lines. Click OK. Now we created mesh. Let's check the attributes of the mesh. Okay. I'm going for this option. See here, first element is created between node 1 and 2, and it has a cross section of 400. Second element is created between node 2 and 3, and the cross section is 200. Okay, everything looks good. Click OK. So now I want to apply boundary conditions. So you need to fix these 2 points now. So I'll go for loads. Let's create the load step. Sorry, analysis type, static. Click OK. Apply loads. Let's select loads option. Okay. So here I'm going for apply option. Under structural, let's pick the displacements. I need to fix these 2 ends. So you can apply it on key points or on the nodes. So I will pick key points. Select these 2 key points. Click OK. See, I need to fix all the degrees of freedom now. Let's opt for all degrees of freedom. If you don't fill anything here, it will assume it as 0. Click OK. So these 2 ends are now fixed. So after this, I need to apply a force now at node 2, at key point 2. So I'll apply a force on key points. Let's select the key point here. You can also mention the number if you know the number. So when I click it now, see the key point number 2 is selected. Click OK. So here we are going to apply the force along the x-axis now, and it is in the positive x direction. So I will add a value there, like -10 kilonewtons, or make it 1 kilonewton. That's right. I want to change it into newtons. So 1000 newtons. Click OK. See this. I think it is in the wrong direction. So let me change the orientation. So delete the value, delete that particular force. On key points, select this, click OK. I'll use all, click OK. Once again, I want to plot elements. Okay. Let's reapply. Use force on key points. Setting key point 2. Yeah, it should be positive, no? I accidentally put it as minus. So delete that value. Click OK. So now it looks good. So I'm done with the boundary conditions and it is ready to solve. Okay, go to solution, use solve option and use current load step. So you can observe the change now. Now only the degrees of freedoms are UX, UI and UZ. Okay, you don't have rotations. So each node has only 3 degrees of freedom. In the previous case, in case of beams, each node has 6 degrees of freedom. Click OK. So the solution is done. Close. Now you can view the results. Okay. I want to plot the results. Initially, I want to see the deflection. So I'll offer under plot results now. I want to go for model solutions. Use vector sum. Click OK. See, the value is maximum here. You can also compare this with you are unable to view the change, displacement. So it's better to go for counter plots. Okay. So maximum deflection is will be at node 2 now. The maximum value is 0.0039. So 0.0039 is they are expressed in terms of millimeters. Okay. These two ends are fixed, so that's why deflection is 0. Okay. You can also find the find the stresses. I'll go for Cornish stress. Click OK. So this is the value. X component is the normal stress. Okay. So here you can also list the results. Element solutions, stresses, Cornish stress. Click OK. So these are the stresses that are induced in the element. Any doubts? So stress is nothing but the equivalent stress. So if the value of the equivalent stress is less than the yield strength, then the design is safe. If the value is more than the yield strength for ductile materials, we consider the system to fail. So with this, I just want to end this session. If you have any doubts, you can ask me.